Vaporization and vapor pressure. Here we have a beaker of water. These water molecules are moving around. An interesting quote is, "It's a wild dance floor there at the molecular level." Roald Hoffman said that. So these guys, it's just like a mosh pit. These guys are dancing, they're having a good time. When you leave water in an open container, it evaporates, doesn't it? And so some of these water molecules are going to escape. Most of them are going to stay here. They're held together by hydrogen bonding, dipole-dipole forces, and dispersion forces. But some of them escape. When things go from a liquid state to a gas state, that's called vaporization. And when they go from a gas state to a liquid state, that's called condensation. So here we see this water molecule and this one in the gas state are on a path to collide with the surface. Once they hit, they're going to get stuck. And so that's condensation. So we have evaporation and condensation. The temperature of the water is an indication of the average kinetic energy of the water molecules, but it's an average. So there's some with higher energy and some with lower energy. So here's a distribution curve, the blue one at a lower temperature. And this line here represents the minimum kinetic energy needed to escape. So how can a water molecule escape into the gas state? It has to have enough kinetic energy, be moving fast enough that it can break loose from those attractive forces that are holding it in. I think of this as Red Rover. That's not what I meant to push. Do you guys ever play Red Rover?
Yep.
Yeah, they don't let them do that anymore. Too many broken wrists, I think. Or just the fear of, it's amazing what my kids cannot do during recess at school. And yet, everybody's so outraged that kids are getting fatter and fatter. It's because you won't let them do anything because they might get hurt. Hello. Anyway, so this is like a Red Rover line up here. Red Rover, you got a line of kids holding hands, and you've got a line of kids on the other side of the field holding hands, and then they say, Red Rover, send Sally right over, right? Sally comes running across, and she's trying to break through your arms, right? Fun game. A little bit violent. So what does it take to break through? Well, you have to have enough kinetic energy moving fast enough and way enough to be able to break through the grip of the people that you targeted, right? If those people are really strong, have a strong grip, you might just kind of bounce off, right? If they're weak, they don't hold on very tightly, then you'll go through, maybe even if you're not going very quickly. So think of kindergartners in the line and maybe the O-line for the Fresno City football team, right? Which one's harder to break through? Those football players, right?
I just think it'd be funny to watch a kindergartner hurling a lot of football players holding hands.
Well, the O-line, he might be able to just duck under, and they might be too slow to bend over. I don't know. So at a lower temperature, there will be a few molecules that have enough kinetic energy to break through. They have to have enough kinetic energy. They also have to be able to get to the surface, right? If you've got one down here that's moving real fast, he can't escape because he has to be at the surface. So there's two things going on there. If we increase the temperature, that's the equivalent of having those children running across run faster. Higher temperature, we've got more molecules that have enough energy. And so the rate of evaporation will go up because there's more molecules that can escape. Does that make sense? We know from life experience that water evaporates faster when it's warm than when it's cold, right? Why do we have heat in the dryer to dry our clothes? Because it makes them dry faster. Well, why is that? Well, it increases the rate of evaporation, causes the water to evaporate faster. Another way to increase the rate of vaporization is to increase the surface area. So the molecules have to be moving fast enough, but they also have to be able to get to the surface. So if you increase the surface area, they'll evaporate faster. The other thing about the surface is that those molecules are held less tightly than the ones on the interior. So the ones on the interior are holding together more strongly. So we see that liquids with larger surface areas are going to evaporate more quickly. So you think about 2 glasses of water, you leave one on the table, you spill one on the floor. Which one's going to evaporate faster? The one that's spilled on the floor. It's got much more surface area. It'll evaporate more quickly. The strength of the intermolecular force affects this as well. So that's how strongly the people holding hands are doing so. How strong is their grip? Stronger grip, lower rate of evaporation. So we've seen this word volatile before. Volatile describes a liquid that vaporizes easily. So probably has weak intermolecular forces. Non-volatile is a liquid that does not vaporize easily. Those are relative terms. There's energy involved in vaporization. If we took that beaker and we insulated it so that heat could not come in from the surroundings, let's think about what's going on. Which particles are evaporating? The high energy ones or the low energy ones? The high energy ones. So we've got this average kinetic energy, and we're losing all the high energy molecules. What happens to the average? It goes down. Evaporation of water causes cooling because it's the higher energy particles that leave. When the water is not insulated from its surroundings, you don't see the temperature dropping significantly, but what it's doing is it's pulling energy in from its surroundings. You get water on your hand or you get sweaty, and then you get a little breeze, and it feels cool, right? It's cooling because it's sucking energy, thermal energy from your skin into the water molecules, which evaporate and take it away with them. So sweat cools you off. Vaporization is an endothermic process. Any questions? Condensation is the opposite of evaporation or vaporization. Evaporation is an endothermic process. Condensation is an exothermic process. When things condense from the gas state to the liquid state, they release a great deal of energy. Steam can cause a much worse burn than hot water. When steam condenses on your skin, it releases a great deal of energy. The energetics of vaporization play a big impact on our climate. Here I pulled some data from, these are average daily temperatures in the month of July, averaged from 1971 to 2000. So here's Fresno, here's San Francisco. Average high in Fresno, 96.6 degrees Fahrenheit. Average in San Francisco, 68. The low, 66 and 54. What's really interesting is the difference. So in Fresno, the average difference between the high and the low, 30 degrees. In San Francisco, 13.8. The temperature does not fluctuate as much from the high of the day to the low of the day. And that has to do with vaporization and condensation of water. So San Francisco is on a peninsula. It's surrounded by the ocean and the San Francisco Bay. Water everywhere. Can't drink it, but it's there. So the sun beats down, the water heats up, but it also vaporizes, evaporates, and absorbs some of the energy from the sun. And so the temperature does not get as warm during the day. Then the sun goes down, and the water starts to condense out of the air, and it releases energy. And so it doesn't get as cold at night either. Here, where the climate is very dry, we don't have a lot of water, we see much bigger fluctuations. You go someplace like the high desert, and you can see even larger fluctuations. It's all due to humidity and water in the area.
Or you can go hang out on Mars.
Pardon me?
Or go hang out on Mars.
Or you could go hang out on Mars, yeah. Where apparently there used to be some water, but there isn't anymore. Well, if there's energy involved, we're going to talk about measuring it, right? Yeah, here's the numbers. Okay, so heat of vaporization, enthalpy of vaporization, the amount of heat needed to vaporize 1 mole of liquid at its normal boiling point. So taking a mole of water, liquid, and making it into a mole of steam requires 40.7 kilojoules. Heat of vaporization is always positive. It's an endothermic process. It is somewhat temperature dependent, but not very strongly. So here we look at water. Heat of vaporization at the boiling point is 40.7. At 25 degrees Celsius at room temperature, it's 44. A little bit higher, not much. And here we've got isopropyl alcohol, acetone, and diethyl ether, and we see their heats of vaporization are lower than water. When a substance condenses, it's the opposite process, and the same amount of heat is involved, it's just the direction's different. So if you take a gas, 1 mole of gas, 1 mole of steam, and condense it into a liquid, it releases 40.7 kilojoules per mole. This can be used as a very nice conversion factor. So let's calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. Well, we're going to need the heat of vaporization. And the heat of vaporization is not something you need to memorize. It would be given to you on an exam. So here it is, 40.7. So I'm going to write that down right away before I forget. Delta H, heat of vaporization is 40.7 kilojoules per mole.
It's negative, right?
Well, it depends on the direction. If we're vaporizing, it's positive. If we're condensing, it's negative. And then I've got 2.58 kilograms of water. So I've got kilograms of water, and I want to end up with kilojoules. What do I need to do in between? Stoichiometry? Well, not really. Dimensional analysis. Same thing. Very similar. So this is kilojoules and moles, right? So if I had moles, I could get kilojoules. So before kilojoules, I need moles. And there we've got kilograms. Molar mass is generally grams, so I need to get from kilograms to grams, and then to moles, and then to kilojoules. .58 kilograms. I'm going to go to grams, get kilograms in the bottom. I go to moles, got grams in the bottom. I go to kilojoules and moles in the bottom. I know some people think, oh, I've got an easier way. Yeah, well, I've seen your tests and it's not working.
Ouch.
Just try it, please. Just try it. So, kilograms and grams. Some of you are still struggling with this. Kilo stands for 10 to the 3. I've got kilo on the bottom. I'm going to write what it means on the other side of the line. 10 to the 3. So 1 kilogram is 1 times 10 to the 3rd grams. Grams to moles, this is the molar mass of water. 1 mole weighs 18.02 grams. You can calculate that. I've just got it stuck in my head. And then here's the new thing. So the heat of vaporization relates kilojoules to moles, 40.7 kilojoules per 1 mole of water. So 2.58 times 183 divided by 18.02 times 40.7. 5827.19 kilojoules. How many sig figs should that have? 3. 5,827 is not the same as 583.
Just do scientific notation.
Scientific notation is the best thing. So some of you are good with this and you can round it to 5830, that's fine. If you're not good with that, do scientific notation. 5.8, okay, I need to round the 2. It's going to round up to a 3. There's my 3 sig figs, times 10 to the, and then look, how many places did I move the decimal? 1, 2, 3. It's a big number. It's a positive exponent. There we go. Now, there's a shorter way to do this part. So instead of writing it out like that, you could say, well, 2.58. Instead of writing kg, I'm going to write what K means. K means 10 to the 3, and then grams. If that makes sense to you, go for it. If it doesn't, do it this way. Any questions? Well, you talked about an open beaker. What if the container is closed? So here we have an Erlenmeyer flask with a stopper in it. So the water begins to evaporate. As it evaporates, we get more and more water molecules in the gas state. They do what gas molecules do, and they bounce around in a straight line until they run into things, and then they bounce. That's when they bounce. Eventually, some of them are going to start colliding with the surface. That's condensation. Here, there's no condensation because there's nothing up here to condense. The rate of condensation is going to depend on how many molecules are up there in the gas state, right? The more molecules you have up here, the more condensation you can get. The rate of vaporization is going to be the same. This Erlenmeyer flask is just sitting there. The temperature is not changing. The surface area of the water isn't changing. The strength of the intermolecular forces in water is not changing. So the rate of evaporation stays the same. But as more and more evaporates, the rate of condensation increases until you get to a point of equilibrium, where the rate of evaporation is equal to the rate of condensation. So you've got molecules leaving and molecules coming at the same rate. It's an equilibrium. It's a dynamic equilibrium because it's not the same molecules in the gas state. There is still evaporation going on. There's still condensation going on. I think of a large airport in the middle of the day. And if you counted the number of people in the airport, it would probably be fairly constant. But it's not the same people, right? There are people departing and people arriving. But if the rate of arrival and the rate of departure is the same, you're going to have the same number of people there, but it's different people. Any questions? So if we look at the rate of evaporation and condensation over time, initially when it starts, there's no condensation because there's no gas molecules to condense. The rate of evaporation stays constant because nothing that affects it is changing. The rate of condensation, though, increases because as you get some evaporation occurring, now you have gas molecules above the liquid and they can condense. And so this is going to continue to increase as evaporation goes on until we reach a point where they're equal. If the rate of condensation is equal to the rate of evaporation, the number of gas molecules is going to stay the same. And so the rate of condensation cannot increase anymore. Gas molecules exert a pressure, right? We don't usually talk about concentration of gas particles. We talk about the pressure of gas particles. So as the liquid evaporates, we start to get a vapor pressure. That's the pressure of the liquid in its gas state. A higher vapor pressure is going to mean that you've got weaker intermolecular forces. Because weak intermolecular forces would give you a larger rate of evaporation. More evaporation, more molecules in the gas state. So what we call vapor pressure is the pressure of a gas in dynamic equilibrium with its liquid.
So acetone, higher vapor pressure than water?
Acetone will have a higher vapor pressure than water. Yep. And the vapor pressure of a given substance is only dependent on the temperature. When we had Dalton's law of partial pressures and we were collecting gases over water, you always have to subtract out the vapor pressure of the water. It depends on the temperature of the water.
Is the reason why we use acetone to clean everything instead of water because the forces are stronger?
The forces, intermolecular forces in acetone are weaker than in water, and because of that, it evaporates more quickly. So if you rinse glassware with acetone, it dries quickly, whereas the water takes a while to evaporate. And acetone is less polar than water, and so it will take Sharpie off, and water doesn't. It'll also take off your fingernail polish. I know that's a concern for you.
No problem.
I know. Well, what if we mess with that equilibrium? So here we have a piston with liquid pentane, and we've got an equilibrium established here between pentane in the gas state and pentane in the liquid state, dynamic equilibrium. If we increase the volume of this cylinder, the volume of the liquid doesn't change, but the volume of the gas changes. When you cause the gas volume to increase, what does that do to the pressure? It goes down. Pressure goes down when you increase the volume. So the pressure has gone down. The pressure is related to the concentration of the gas molecules. That affects the rate of condensation. Fewer gas particles per unit volume. Condensation goes down. It doesn't do anything to the rate of evaporation. So the rate of evaporation stays the same, but now the condensation goes down, and so we reestablish the vapor pressure that was there before. As long as there is liquid in the container, the vapor pressure will be the same once it reaches equilibrium. If we take that cylinder and we compress it, we make the volume smaller. We increase the pressure of the gas. Now we increase the rate of condensation. Doesn't do anything to the rate of evaporation. We've got more condensation, and so we lose pressure, and it'll go back to what it was. Le Chatelier's principle says that a system in equilibrium, when disturbed, will react in a way to reduce the disturbance. So equilibrium does not like change. If you try to change it, it'll fight back and do whatever it can to reestablish the way things were. Status quo, we're good with it. Okay. So vapor pressure does depend on temperature. So we see here water is this red line. As we increase the temperature, the vapor pressure increases. Because what's happening as we increase the temperature? The rate of evaporation becomes larger. It evaporates more quickly. And so the rate of evaporation ultimately determines the rate of condensation at equilibrium. So we get higher and higher vapor pressure. Get a small change in temperature, we can get a large change in vapor pressure. You'll see all of these go up, but the curves are different. The boiling point of a liquid is the temperature at which the liquid's vapor pressure is equal to the external pressure. When that happens, the molecules in the interior now have enough energy to break into the gas state. So they don't have to be at the surface anymore. They have enough energy to break into the gas state down here in the interior of the liquid. And so what happens is they'll form these little pockets of gas or bubbles. Bubbles are less dense, and so they rise quickly to the surface and pop.
That's why when you're boiling, it looks like water. It looks like air is just forming at the bottom.
Right, it looks like air is forming. It's actually steam. It's water in the gas state. Yeah, it's not air bubbles. They look exactly like air bubbles because both of them are invisible. They're just these bubbles. So the boiling point is actually going to depend on the external pressure. The normal boiling point is the temperature at which the vapor pressure equals 1 atmosphere. That's what temperature would it boil at sea level? That's 100 degrees for water. Here's 1 atmosphere pressure, 760. So water boils up there. If you have a lower vapor pressure, let's say you only had 400 torr, then water's going to boil around 80 degrees Celsius. If you increase the pressure, then it will boil at a higher temperature. So if we take water at 20 degrees Celsius and we add heat to it, the temperature goes up. This makes sense. It gets to the boiling point, it starts boiling, the temperature doesn't rise anymore. the temperature stays at 100 degrees Celsius. You turn up the heat. I want it to get hotter. All that's going to do is make it boil faster, boil more. Okay? It's not going to increase the temperature. You cannot get higher than 100 degrees Celsius with water at room temperature. Water at atmospheric pressure. It will not increase in temperature until you've boiled away all the water. Then the steam can rise in temperature.
So it hangs out at boiling. Is that because all the molecules that you're measuring in the water, they're waiting to jump out, so they can't get any hotter than?
Well, I think of it this way. So remember we talked about when you're evaporating something, it's the higher energy molecules that are leaving, right? And so the ones that are left have a lower average then. If you're not adding heat to it, evaporation will cool things. That's how a swamp cooler works. Here we're adding heat. When we're adding heat, it's still, anything above that threshold will escape. But it's an average kinetic energy at 100 degrees Celsius. So there are some above and some below the amount of energy needed to escape. So what's happening is we add more and more heat, we're just providing energy to the ones that are too slow to escape. So it'll happen, the boiling away will happen faster at a higher temperature, but it will not be I'm sorry, that was bad. It will boil faster, boil away faster if you have the temperature of the heat source higher. But the water will stay at the same temperature because everything that gets above the threshold leaves. And so what's left behind is still at 100 degrees Celsius. None of it goes into increasing the kinetic energy, the thermal energy of the water. It all goes into causing molecules to escape. So when you're cooking something, right, if you want to cook it faster, you need higher temperature. If it's at boiling water, it doesn't matter how fast it boils. It's the same temperature. How could you cook something faster in water? Salt will only change it a tiny bit. Pressure. Pressure cooker. You heard of those? How does that make your food cook faster? When you put pressure on this system, it increases the boiling point of the water. So here it's boiling at 100. If you allow the pressure to increase by putting a lid on it that seals, you can get water to boil at a higher temperature. Then your food's going to cook faster. We're going to save that for after spring break.